here's how it can be used. Here's what it will do to the world as a consequence of its reality. And not just make energy, by the way. It also has it has the prospect of getting rid of radioactivity through transmutation. The Russians have been exploring that, really fantastically clever. I mean, they have Chernobyl area terribly contaminated. They're discovering that bacteria will accelerate the decay rate of cesium. So they just inoculate the bacteria in the soil and let it do its thing. And instead of taking 30 years, it only takes 5 years to get rid of it. See? And, you know, things like that are in the offing. What they do is take a solution of cesium-137, has a 30-year half-life. Half of it goes away in 30 years. And so they put these bacteria in, and they have a variety of bacteria, and the more complicated the culture, the faster this happens. So they're still exploring what the most effective thing is. And then they measure the rate of the radioactivity, and that radioactivity drops with time faster than it would otherwise. Now, it isn't quite clear what it's converting to. Probably it's putting a proton into the nucleus, converting it to the next element, and that element is not radioactive. So you're converting a radioactive element, which has energy in it. That's why it's radioactive. It's got energy in it. The energy is trying to get out of the nucleus. It gets out by a gamma emission. But when the proton goes in, that energy is released immediately, and the element that results is not radioactive, it's stable. So it essentially gets rid of that energy immediately. But it takes a little while for it to find all of the cesium, so it takes, you know, it doesn't happen instantaneously. And so that's what they do. Then they say, okay, we'll take this culture and we'll spread it around in the soil. And we'll use bacteria that will live in soil. And whenever it finds a cesium atom in the soil, it will put this proton in and the cesium will go away. And so now, instead of waiting for 30 years for this cesium to pop off, it'll pop off right away as soon as the bacteria finds it. That may take a little while because, you know, bacteria is here and the cesium's here, and they have to wander around, and finally they find each other, and that happens. Anyway, that's one possibility. I don't know if they've actually tried to implement it in the soil. I mean, there's a real problem there because you have to have a bacteria that can live in the soil, and then you have to have it somehow or another high enough concentration that can find the... And it isn't just cesium that's in the soil. There's other things that are in the soil that it could decide to interact with instead. I mean, why would it go after cesium? It might go after something else, and then, of course, kill itself, or who knows what happens. So actually applying it is not easy, but the fact that it could conceivably happen is the significant thing at this point.
Is that why you call that cold fusion?
I call it cold fusion because it requires the same nuclear active environment that causes fusion. It's just another variation. It's transmutation. We know that transmutation occurs in the cold fusion environment. We've seen this. There's lots of evidence for that. So the nuclear active environment, whatever it is, has the ability to initiate a number of different kinds of nuclear reactions. One makes helium and heat, another one makes tritium, another one does transmutation. So there's a variety of things that can happen in that environment. The bacteria, apparently for whatever reason, within the protein of its structure, has a nuclear active environment available to it should it wish to use it.
Wow. Now,
I mean, back in 60 years ago, Coveran in France came up to the same conclusion based upon chickens and seeds and things like that. And he published a number of books on the subject. And he says that, for example, if you take a seed and weigh it, and you germinate it, and then analyze the plant has different elements in it than the seed did, even though it was raised in distilled water. So where did these other elements come from? They had to come from the elements that were originally in the seed being transmuted into these other elements that you later found.
Mm-hmm. Yeah, okay.
Well, he made that case, and he studied this, wrote a couple of books on the subject. People laughed at him. But he started people thinking about this. Did it with chickens, he did it with seeds, he did it with various plants, came up with all kinds of ideas. Then the Japanese, not too long ago, did the same thing with yeast and various single-cell organisms, not bacteria, but yeast-type organisms, and came to the same conclusion. If you put them into a culture that was missing an element they needed, it was missing iron, or it was missing potassium, elements that they absolutely needed for life, they would grow. They didn't like it. They wouldn't grow very well. But when they grew, and you analyzed them, you discovered that they had made that element that they needed from the elements that were available that were not the element that they needed. See? Well, this guy was sort of laughed out of the club also. Then the Russians came along with a study where they converted manganese to iron by adding a deuteron using a bacteria. And they did the study using the Mossbauer effect to detect the iron. That study was so unambiguous, so absolutely clean, clear-cut, that it made it absolutely, without a doubt, that they in fact had initiated a nuclear reaction with using a bacteria. So then they said, well, okay, if we can do that, why don't we see if we can get rid of radioactivity? So then they went the next step that we just talked about, and found, yeah, you could. Well, meanwhile, the rest of science laughs them, except in the Ukraine, where they're from, and where Chernobyl is located. They're heroes. They're doing something actually useful. The rest of the world can laugh all they want, but that the bacteria, the biological end of this thing, most people simply cannot believe. And if you say, okay, if that can happen in bacteria, the bacteria must have the same nuclear-reactive environment that you have in palladium. What is that? So therefore, the theory starts to get very limited, and then you have to say, okay, whatever the theory is, it has to describe the same kind of nuclear-reactive environment in palladium as this bacteria has available in its enzymes.
Yeah.
Well, boy, all of a sudden, this thing gets really interesting.